Okay, so thank you for inviting me for this celebration for our friend and master. So before preparing these slides, it came in my mind a very famous phrase from a Russian writer, Mikhail Bulgakov, that says that commented on the importance of critical thinking and the interest in discussion, even never-ending discussion in a scientific dispute. I think that Boris has all these talents, and as you see in the photo, this was taken in Siena in '98. You see Vladimir Kharitonov, I think so, Boris, myself, Osvaldo Grasselli, Vladimir Kuchera, and an unknown lady, I don't know, here. Maybe you, Boris, can remember. I don't remember who is the lady was. Okay. So as you can see, Boris not only is interested in scientific research, but also in good food and good Italian wine. Okay. So thank you for being here, and Zdiem Razdanie, Boris. So I would like to motivate the study of positive switcher systems with some very simple applications. Then I will talk about stability and stabilization, performances and optimization of such systems. With an example, I would like to give some result, a very recent result on sufficiency upon tracking condition for stochastic optimal control problem via convexity. And then a conjecture on stochastic consensus that, I tried to prove this conjecture for a couple of years without any apparent results. So maybe in this audience, someone can give me some good hints. Okay, so let's take, for instance, this building with 3 rooms. Xi are the temperature in the 3 rooms, and there are 2 doors that can be opened and closed. So in principle, you have 4 configurations here. And if you write the model of the system, you end up with this positive system, switch systems. X dot is equal to A sigma plus B U. And for instance, you can address the problem of maximize the temperature. Of course, if you want to maximize the temperature in the first room, the best thing you can do is just to close the 2 doors. But if you want to maximize the temperature at finite time in the 3rd room, the solution is not going to be a stationary condition. You have to continuously switch between open and closed doors in order to achieve the maximum. Okay, so this is an interesting question. Look at this other example, traffic congestion control problem. You have 3 main roads, A, B, C. You have 6 traffic lights, red or green status, 3 buffer variables, and 3 symmetric configurations. So in the figure it's depicted the first one, the other 2 are given by symmetry, just by rotating. Okay, so you end up with a positive system. X dot equal to A sigma X. Sigma can take values 1, 2, 3. B is the inflow traffic, for instance. And for instance, you want to stabilize this system, or let's say to minimize the buffer variables in some sense. And this is interesting because if you look at the system, you don't find any convex Hurwitz combination of the 3 modes, A1, A2, and 3. And so if you want to stabilize it, you have to, let's say, continuously switch with a dwell time between the 3 configurations in order to stabilize it or to minimize the variable, the buffer variables when B is different from 0. Okay. Another example is let's say, this very simple fluid control problem, in which you have 2 sluice gates from the first reservoirs to the second, from the second to the third, that can take 3 positions, fully open, partially open, and closed. And you end up with, after linearization, with this system. these switch systems, and maybe you want to look at the emergency emptying strategy. And of course, what you can see here is that if you want to, let's say, if you want to quickly empty the reservoirs in case of rainfall, let's say, what you have to do is not just open the two sluice gates, but I mean, because otherwise there could be some big inflow in the downstream reservoirs. So you have to switch also in this case. Okay. Here is a topic that I was working on for a couple of years on HIV system. You know that there are, let's say, very, very efficient antiretroviral therapies. The problem is that you have, let's say, viruses with, that are more or less susceptible to therapies, and so you have to continuously change the drug combinations in time in order to shrink the infected T cells. Okay? So if you write these models, for instance, in this case you have 16 genotypes, and you have two therapies, or two mixture of therapies, you end up with a simple linear model in certain circumstances. Okay, so the system is actually non-linear, but then in certain circumstances you can think it as a linear system. And the problem, you can, for instance, put a cost, a final cost, and try to minimize by switching the therapies, minimize the total viral amount, and in so doing mitigating the viral load over time. Okay, so there are a lot of research on that going on in these last years. Here you have a chemical system where S is the stoichiometric matrix, G is the rate, reaction rate, G0 is a constant vector. This is a nonlinear system, inherently nonlinear, but I mean, you can study the boundedness of solutions of this system by looking at this differential inclusion here, depending on the interval of the parameters of the system. And what you know is that any solution of the nonlinear system are also solutions of this differential inclusion. The converse is not true. Any solution of the differential inclusion are let's say, a superset of the solutions of the nonlinear system. But in any case, by looking at the switch systems that is inside this polytope here, you can study the stability of the nonlinear system, for instance, under arbitrary switching, by looking at the switching system. Okay. Last, let's say, example: distributed power networks. You know that I mean, there is a so-called Foschini-Milanowitz algorithm for distributed for distribution of powers along the users, and you end up with a model where Pi are the powers at the IFE receiver. These are gains, and these are let's say what is called sink, which is the interference let's say ratio, the channel gains, and the noise, the thermal noise at the receivers. Okay. And then you end up with this model here. This is just a way to distribute power. You want to achieve the equilibrium, which is the ratio between this and this, in some sense. And the fact that these gains Gij depend on the linear detector coding properties, but is affected by path losses, shadowing, multipath fading. So you end up with a switch system here, where sigma is now, let's say, a stochastic process, is not a control variable. Okay. Okay. So looking at the previous example, but I could have put more than that. we end up with systems that takes this form. Okay, so we have usual differential equations where matrices A11, A12, A21, A22, and so on and so forth are Metzler matrices. So this means that the off-diagonal elements are entry-wise, off-diagonal entries are non-negative. Matrices B, C, and D are non-negative. So this is at all effects is a positive system in the sense that if your initial state is in the positive orthant, the positive orthant is positively invariant, so X remains in the positive orthant, and if W is a positive, let's say, a deterministic or even stochastic process, X is positive and Z is also positive, entry-wise positive, okay? So here you have two switching signals. One is sigma, that is a stochastic disturbance, coming from a Markov chain with a certain transition rate lambda, okay? And gamma is your control switching signal, okay? So you can, let's say, address a lot of problems related to this system of stability problem, optimization problem, and so on. And we will look at some of them very, very quickly. Okay. Being a stochastic process, you have to, let's say, clearly decide which kind of stability you want to achieve, to test. Okay. So for stochastic processes, you have many characterization of stability. Moment, let's say, stability, mean square stability, second order moment stability, almost sure stability, which means that the probability of the state transition goes to 0 is equal to 1. But for a positive system, it is also sensible to look at what we call mean stability. And this mean stability, means that the expectation value of the state goes to 0 for any initial state and for any initialization of the probability vector of sigma. Okay. So the problem can be, this is a sensible definition for stability, for a positive system. Of course, for non-positive system, this, signifying almost nothing, because if the expectation values go to 0, you can have oscillations around 0, of course. But for if X is positive, the fact that expectation values go to 0 means that almost all trajectories go to 0. So this is a sensible concept for positive system to be studied. So you have analysis problem, check mean stability for any possible gamma, switching signal gamma, or design problem, find gamma that is such that the closed loop system, or the controlled system is stabilized. And this also depends on the information that is available to the designer, because gamma can depend on the state, of course, if you can measure the state, can depend on sigma, if you can measure the sample path of the stochastic process, or can be mode independent in the sense that you don't know sigma, you have maybe to reconstruct it from observations, and this means that you are going to have identification of a hidden stochastic process in some sense. Okay. The good news about mean stability is that for constant gamma, mean stability is equivalent to Hurwitz stability of a big matrix. This matrix, this is a Metzler matrix, so checking Hurwitz stability is very simple, it's a linear program. And okay, as far as performances, we can consider many performances, but the one we considered so far are these two. The L1 induced performance, which means the ratio, the worst ratio over all disturbances of the L1 norm of the output and L1 norm of the input. L infinity induced performance means the worst case of the peak-to-peak, let's say, norm, which is the expectation value of Z over all channels, expectation value of the input over all channel. Okay, there are two different, let's say, performance criteria depending on the application at hand. Also, in this case, you can analyze and try to find the worst gamma, or in the design problem, find the best gamma in order to minimize this performance index, and depends on the available information to the designer. Okay. From now on, we consider W as a deterministic disturbance, so you can drop off the expectation value in the denominator of these two formula, and we'll stick with the first one, which is this one, because it's easier to be treated than the second one. Also in this case, for a given gamma, given and constant, you can compute in a very easy way the performances. The J1 and J infinity are related to a transfer function, a big transfer function of let's say a sort of average transfer function of your stochastic system, by taking the one norm or the infinity norm. These are just a numerical norm of the transfer function computed at zero frequency. Okay? And this can be done by a linear program, in the sense that you have, for instance, this result that J1 is less than a given rho if and only if there exist positive vectors, entry y positive vectors Vi satisfying these linear inequalities here. Everything is linear here. Lambdas, the lambdas are given, the matrices are given. You have to find V1, V2, V3, V4, and so on. R is fixed in order to solve this linear program. Okay, and you see this is just let's say an extension of what of the, let's say, the small gain theorem in some sense for positive systems, positive Markovian systems. The main technical tool here is what we call co-positive stochastic control Lyapunov function, that assume this form for the L1 norm. Assume this form, so it's the minimum over all modes of a minimum over all possible gamma of a vector V sigma R transpose X. This is a positive vector, so this is a positive function. You take the minimum. This is a stochastic function here, so you have to compute the infinitesimal generator. The expression is like this, and you end up with this formula here. So you see here that differently from, I don't know, H infinity norm for a standard system and so on, you have a sort of separation here, because we have the sum of two terms, one depending on the state here and one depending on W and Z. So these translated the inherent gain between nature and the performance output here. And here you have this term, and if you find vectors such that this first part is negative, okay, using Dynkin formulas, stochastic formulas for this infinitesimal generator, you end up with upper bounds to the ratio between these two guys here. So this is the main spirit of that on L1 control. And as I said, there is a separation here that is not present when you deal with L2 to L2 control, for instance, because the worst disturbance for L1 control is an impulse. Does not depend on the state. The worst disturbance does not depend on the state, like in H infinity control. In H infinity control, the worst disturbance is state dependent. Okay? Here, the worst disturbance, if you make all computations, does not depend on the state on the state of the system. Okay. So we have a bunch of theorems for stabilization. We have three versions for stabilization. This is a bilinear version in the sense that if you have to look for positive vectors Vi, R, and Metzler coefficients phi rs satisfying these inequalities. You see that these inequalities are not linear because we have the product here between phi and v. Okay, but I mean by randomized phi or looking at phi, I mean trying with many phis, you may be able to find these vectors vi's. And then if you apply this switching law here, which is the argmin of these functions here, this is a mode-dependent switching law because it depends on sigma and also x, okay? This switching law makes the closed-loop system mean stable, okay? There is also a linear version of this. Linear version assumes the existence of a map for each sigma. You may find a static map gamma equal to g of sigma that is and vectors vi's that satisfies these inequalities. Everything is linear here. You have a finite number of possible maps, so you can test this very easily. And then you put these vi's in this formula here. You obtain this vector, and you switch according to this rule based on these vectors here. Okay. And this is going to make your closed-loop system mean stable. More difficult is the case of mode-independent, because in mode-independent control, you don't have availability of the sample path of the stochastic signal sigma. You don't have sigma, and you don't want to identify it or whatever. So we arrive to let's say a sort of robust problem in the sense that you need to find the VI's, the positive VI's, and the matrix Q satisfying these linear conditions here. Okay, this is also nonlinear. You see the product of these two. But if you take this concave convex problem here, you take the min max of this, which is state dependent, by the way. So for each x, you have to solve this relaxation, min max over convex set. These are the simplices of vectors mu and ni, and you find this hij of x, and then you switch according to this. I mean, this is not just a switching rule. This is this is a sliding mode, by the way. This is just a sliding mode. Mu star is a sliding mode. Yeah, sure. Sorry. Okay. So we have the analogous of these three theorems for, so I will skip them. So for L1 induced norm, so this is the bilinear version. Okay. And this is a switching rule. This is the linear version with the map G of sigma. Okay, so this is switching. And you obtain these upper bounds here, and then you have the mode-independent version for L1 induced norm. Of course, you can also address the problems, the same problems for the L infinity norms. Okay, so this is an example. You have these four matrices. You have the infinitesimal rate generator lambda. You have the B's matrices, C matrices. In let's say in open loop, you have certain norms. So you want to increase, to decrease this norm by switching, and you can do that. I mean, here you have realizations, 20 realization Monte Carlo simulations of these using static map, using state feedback. Here is a state feedback. Oh, this is just stochastic sliding mode in some sense, okay? In the sense that depending on the conic sector in the state space, you have a switching law that depends also on sigma, on the sigma, okay? So convexity, just a couple of minutes. Convexity for diagonal switcher system. This is a recent say work that was also applied to HIV infection. So you have your dual switcher system here. You put it in a polytope here. The restriction is that the control affects only the diagonal entries of these matrices. You have a cost, a final cost, so at all effects, you want to minimize it, so it's the so-called Meyer problem, optimization problem. What we proved is that this functional is convex with respect to the use, okay? And this is given by the fact that the system is a positive system, and so on. Okay, so in this paper there is a proof of the convexity. So this means that any Pontryagin solution of the optimal control problem is are also optimal controls, because there is this condition of convexity, and you can solve it in open loop, of course, by looking at by using some gradient method and so on. So this is very interesting. Last, with the conjecture, okay, this is a recent research with a couple of colleagues in my department. Assume you have n agents, m discrete state for each agent. So this can be a telecommunication network, a social network, or whatever you want. All the matrices satisfies these conditions. So the sum of the columns are 0. An agent in state I transmits this information to the neighbors at rate lambda I, and so you have an imitation strategy here, and so the system ends up to be, let's say, a non-linear system. So you have a non-linear system. What we proved for a complete or star graph topology is that you can achieve a probability consensus. Pi is the probability of the agent R, pi s is the probability of agent S. You achieve this formula. What we cannot prove, despite all simulations, is that, I mean, the common vector to which all these agents converges is constant. So you have a fixed point here, pi bar. We know by simulations, let's say, that pi converges to pi bar, but we don't know why. In the sense we cannot prove it, okay? And this opened the way to also control problems. And for instance, in social network, this is very important. You have, let's say, a desired probability for all the users. And you want to, let's say, change the rates, the imitation rates, in order to achieve this consensus equilibrium and so on. So I think I can stop here. Okay, thank you very much. Sorry to be not so late.
One, two short questions, please. One short questions. Why you consider mean stability? Because this system is positive.
Yeah.
This is the simplest way to consider. And, what about mean square stability?
Yeah, we can consider mean square stability also, but you end up, it's more complicated.
And you will not compare results. What gives...
No, mean stability is weaker than mean square stability. It's weaker for these piecewise linear systems. We studied also almost stability that is really important.
You have only sufficient conditions for stability.
Yeah, of course,
Only
yes.
sufficient conditions.
These are only sufficient conditions based on piecewise linear Lyapunov functions.
Thank you. More questions? No questions. Thank you.